So आपको ये I'm giving you the definition of cover of a set. What we mean by a cover. Let XD be a metric space and A be a subset of X. Okay. Full stop. Now, if bold face B sub A, we'll be using this symbol और आपको ये याद रखना है कि किस चीज़ के लिए हम इस्तेमाल करेंगे. If bold face B sub A be the collection of all possible closed balls in XD containing A. समझ रहे आप? Bold face B sub A is going to be the collection of all possible closed balls. जितनी भी closed balls हो सकती है XD में which contain A. Then अगर ऐसा है, if this be the collection of all possible closed balls in XD containing A, then the cover of A, जिसको हम denote करते हैं, denoted by COV of A. This is how we denote the cover of A. Denoted by this symbol is defined like this. COV of A, it is defined as intersection of all the B's which are coming from bold face B sub A. This is how we define the cover. ठीक है? अब में से अब मुझे कोई बता सकता है what would happen if there are no balls in B sub A? That means when the collection is empty. पहले मुझे बताइए, is it a possibility that the collection is empty? क्या ऐसा हो सकता है?
Yes, sir.
कब होगा? हाँ, ये आपका आंसर सही है. कब होगा ये? कब होगी ये collection empty?
जब कोई क्लोज्ड बॉल से कंटेन नहीं करेगी.
हाँ, वो कब होगा वही मैं पूछ रहा हूँ आपसे. If you have a closed ball containing A, it automatically means that the diameter of A is finite.
Yes, sir.
That means A is a bounded set in XD. If A is not a bounded set in XD, then there will not be any closed ball containing this A. So therefore in that case this collection will be empty. And what would be the intersection in that case?
X.
It will be X, because we know that in empty intersection is X. So cover of an unbounded set is X. And it makes sense. The set is unbounded. So cover करना है तो it will be X. लेकिन जो बाकी बाउंडेड सेट्स है उनके लिए आप ये कर सकते हैं. यू कंसिडर, you collect all the closed balls containing that set, take the intersection, you'll get the cover. ठीक है. Now I'll record certain remarks about this cover. पहली remark ये है, COV, cover of A, is always a closed set. बताइए क्यों?
Intersection of closed sets.
Exactly, this is the reason, because intersection of closed sets is closed. Second, A is always contained in the cover of A. It's a subset of cover of A. A is a subset of its cover. और ये भी कोई देखना difficult नहीं है. It follows by the definition actually. If A is unbounded, this is trivial because cover A in that case will be X. A is contained in X. If A is bounded, उस case में A is actually cover of A जाए, it will be intersection of all the balls containing A. And this will be intersection of all the balls containing A. This will be intersection of all the balls containing A. Since the balls are containing A, so A will be contained in the intersection. So that means A will be contained in the cover of A. तो ये भी होता है. हाँ, जो reverse inclusion है, that may or may not be true. Cover of A may not be contained in A. और अगर ऐसा होता है तो ऐसे सेट्स को हम एक अलग कैटेगरी या एक अलग कैटेगरी ही ठीक है, एक अलग कैटेगरी में डील करते हैं. वी कॉल दो सेट्स एज एडमिसिबल सेट्स. A set is said to be admissible if it is equal to its cover. अब ये मुझे बताइए, what will be third observation? These are remarks about this. If you take the cover of X, what will be the cover of X? अगर आप second observation का इसका इस्तेमाल करेंगे, you can immediately see that it is actually X. ठीक है? 4. What will be the cover of the empty set? You can prove this that it is actually equal to 5. The cover of the empty set will be the empty set. If you are in a space with at least 2 points, if your X has at least 2 different points, then you can prove that cover of empty set is actually the empty set. And if there is only one point in the space, वो कोई interest, that's a pathological case, so we can ignore that case. आप समझ रहे हैं मेरी बात? Suppose you have a metric space XG where these underlying set is a singleton set. क्या ये कोई mathematically interesting situation है? नहीं. It's a pathological case, so we discard this. बाकी जो cases हैं वहाँ you can prove that cover of empty set is the empty set. So we therefore treat it. अब हम वो जो pathological case में उसमें भी हम उसको ऐसे ही define करते हैं. We define it as the empty set. वो मैं आपको बता रहा हूँ. If X has 2 different points, वहाँ इसको कैसे करेंगे आप? इसकी justification है, ये 4th remark है. So you take A as phi and assume that your X has at least 2 different points, say U and V are in X with U not equal to V. U not equal to V. अब इसके बाद क्या करिए? You define R as the distance between U and V, और फिर आप you consider these 2 balls. You consider the ball whose closed ball whose center is U and radius is R by 4. Similarly, you consider this ball whose center is V and radius is R by 4. Now you can see that both these balls, this and this, they belong to boldface B sub A, where boldface B sub A is the collection of all possible closed balls containing A. What is A in this case? A is the empty set. Empty set is a subset of every set, so that means empty set is a subset of both the balls. It's a subset of this as well as this. Subset of both the balls means both the balls are in B sub A. So when you take intersection of all the balls in B sub A, this intersection, चूंकि B sub A में ये दो balls भी आ रही है, so therefore this intersection it will be contained in the intersection of these two balls, B U R by 4 intersected with B V R by 4. And what is the intersection of these two balls? It's phi. आ सकता है इन बॉल्स में कोई चीज़ कोई कॉमन एलिमेंट?
नो सर.
नहीं आ सकता है, ये सब सवाल ही नहीं है. ठीक है, because if there is a z which lies in the intersection, let's suppose there is a z, हालांकि ये मुमकिन नहीं है पर आपकी satisfaction के, let's suppose that there is a z in the intersection, तो फिर क्या होगा? distance between u and v, in the first place using triangle inequality, this will be less or equal to distance between u and z plus distance between z and v. Now z lies in both the balls, so therefore both the distances will be less than or equal to r by 4, so therefore the sum of the distances will be less than or equal to r by 4 plus r by 4, which is equal to twice r by 4, and twice r by 4 is r by 2. So आप कह रहे हैं distance between u and v is less or equal to r by 2, which is not possible because the distance between u and v is r. So you'll be contradicting this thing जो आपने यहाँ ये लिया. So we get a contradiction. So this is contained in phi, empty set में contained है तो ये खुद empty होगा, and this by definition is cover. So this is cover of A where A is the empty set. So this you can prove quite easily that cover of the empty set is actually the empty set. So these are some observations about the cover. अब ये जो मैं अभी आपको बता रहा था, A is always contained in the cover, but reverse inclusion may or may not be true. If it is true, we say the set is admissible. ये हमारी होगी next definition. Admissible sets. Let XD be a metric space and A be a subset of X, then this A is said to be an admissible set. इसके लिए बस एक सिंपल से रिक्वायरमेंट है, if and only if A is equal to its cover. ठीक है, so this is the admissibility definition. इसके बाद एक नोटेशन आप रिकॉर्ड करेंगे, या पहले कुछ रिमार्क्स आप देखिए. हमने ऊपर देखा cover of X is X, so that means X is admissible. Cover of empty set is the empty set, so empty set is also admissible. This will be the remark actually. X and phi, the largest subset of X and the smallest subset of X, they are always admissible. Or admissible. Sets. ठीक है. हाइपर कॉन्वेक्सिटी एंड कंप्लीटनेस, हाँ वो मैंने आपके साथ डिस्कस किया. अभी जो है will introduce a notation now. So record this as a notation. We shall use this symbol, script AX. We shall use this symbol to denote the collection of all possible we shall use this symbol to denote the collection of all possible admissible of all possible admissible sets in XD in the metric space XD. हम ये सिंबल का इस्तेमाल करेंगे. एंड बाय द वे एक और चीज़ मैं आपको बता रहा हूँ, ये जो एडमिसिबिलिटी है ना, एज पर सम ऑथर्स ये दे आल्सो रिक्वायर बाउंडेडनेस फॉर एडमिसिबिलिटी. इनफैक्ट जो बुक हम फॉलो कर रहे हैं ना, खामसी की जो बुक है, वहाँ भी शायद आपको ये बाउंडेडनेस रिक्वायरमेंट मिलेगी. एडमिसिबल सेट ऑफ ए इज इक्वल टू कवर. बिकॉज एक्चुअली वो बाउंडेड सेट्स के लिए ना, आपको वो कवर को कंप्यूट करने के लिए पहले तो वो जो B sub A है फॉर बाउंडेड सेट्स, वी नो दैट द कलेक्शन इज नॉन एम्प्टी. वो बस एक फ़ायदा रहता है इफ यू डील विद बाउंडेड सेट्स. बाउंडेड सेट मीन्स यू कैन कैप्चर द सेट in a ball. This is what boundedness means in metric spaces. अब हम क्या करेंगे, अगर हमें ये एडमिस बाउंडेडनेस भी चाहिए, हम तो उस टाइम एक्सप्लिसिटली लिखा करेंगे अब बाउंडेड एडमिसिबल सेट. ठीक है, हम ऐसे, अदरवाइज वी वोंट रिक्वायर दिस बाउंडेडनेस. हाँ, जहाँ ज़रूरत होगी वहाँ हम लिखा करेंगे बाउंडेड एडमिसिबल सेट. और इन मोस्ट ऑफ द केसेस वी रिक्वायर दिस एक्चुअली, दिस बाउंडेडनेस इन मोस्ट ऑफ द थियरम्स. हाँ, फिर मगर यहाँ फिर एक मसला आ गया था. मैं आपको ये बता रहा हूँ बेसिकली, अगर ना ये बाउंडेडनेस आप यहाँ इनकॉर्पोरेट करेंगे तो यू कैन नॉट क्लेम एडमिसिबिलिटी ऑफ एक्स, बिकॉज एक्स मे और मे नॉट बी बाउंडेड. वो एक मसला हो जाएगा फिर यहाँ. ठीक है, दैट इज़ द रीज़न मैं फ़िलहाल ना ये बाउंडेडनेस को नहीं ले रहा हूँ. हालांकि अगर वो बुक जो हमारी जो टेक्स्ट हम फॉलो कर रहे हैं उसमें आपको यहाँ बाउंडेडनेस भी मिलेगी. next we'll record certain observations, या मेरे ख्याल से I'll record this as a theorem. मैं आपको कवर कंप्यूट करने का एक और तरीका अब दे रहा हूँ. Theorem. It will be, let's first record a theorem about admissible sets, right? तो, और by the way एक और चीज़ भी है. अभी मुझे शायद most of the cases, if you have an admissible set, the set is bounded, because if you can write the set as intersection of balls, it automatically becomes bounded. अभी आप ये थ्योरम को देखिए. लेट एक्स डी बी अ मेट्रिक स्पेस x be a metric space and A contained in X be a bounded admissible set. हम ऐसा करेंगे, मुझे एक रास्ता इसमें दिख रहा है. आप ये करिएगा, वो जो कलेक्शन है ना, script AX, we use this collection to denote the we use the symbol to denote the collection of all possible. इसी में आप ये करिएगा, आप collection of all possible bounded admissible sets. यहाँ ये करेंगे आप. So this script AX will be only taking those admissible sets which are also bounded. ठीक है. बाकी जो एडमिसिबिलिटी डेफिनेशन है उसमें वो हम बाउंडेडनेस रिक्वायरमेंट इनकॉर्पोरेट नहीं कर रहे हैं, बिकॉज अदरवाइज विल हैव अ प्रॉब्लम विद एक्स. Be a bounded admissible set. So therefore this A is coming from AX, script AX. Full stop. अगर ऐसा है, if this A is या ऐसे लिखेंगे, if B xi ri such that I varies over some indexing set, say capital lambda, if this be a collection, if this be a collection of closed balls containing containing A शायद इसमें अभी कुछ चीज़ें पेंडिंग है, वही देख रहा हूँ. हाँ, obviously I required certain things for this. मैं इससे पहले एक रिजल्ट ना जो मुझे चाहिए बिफोर दिस, पहले उसी को देख लेते हैं. हम इसमें थोड़ी सी करेक्शन कर रहा हूँ. X be a metric space and A be a part of X. पहले मैं एडमिसिबिलिटी को ही एक और तरीके से कैप्चर करना चाहता हूँ. And X full stop. Assume this A can be written as, assume A can be written, yeah, if sorry, स्टेटमेंट शक्ल जो है, प्रॉपर स्टेटमेंट शक्ल के लिए आप इफ़ लिखेंगे यहाँ. इफ़ ए कैन बी रिटन as an intersection of certain closed balls. मतलब आप ऐसा मान लीजिए कि that there are certain closed balls in X whose intersection is A. If A can be written as an intersection of certain closed balls in X, then the conclusion is this: then this A is an admissible set, is a bounded admissible set. Then A is a bounded admissible set. We'll prove this first. Proof. हमारी assumption ये है कि that A can be written as an intersection of certain closed balls in X. तो मैं पहले यही लिख रहा हूँ. Let A be equal intersection I in capital lambda B xi ri, and A be equal to this, and fancy F be equal to the collection of these balls which you see in this intersection. जो intersection में ये जो balls आप देख रहे हैं ना, इन्हीं की collection हम ले रहे हैं, और the collection is denoted by fancy F. The fancy F is going to be B xi ri. I varies over capital lambda, full stop. Now if boldface B, as usual, be the collection of all possible closed balls containing A, then what can you tell me about the relationship between fancy F and boldface B sub A? Clearly the relation is that this fancy F, this will be a sub collection of boldface B sub A, है ना? because fancy F is also a collection of balls. But the thing is, B sub A is the collection of all possible such closed balls. यहाँ सारी आती है, तो in particular यहाँ ये fancy F वाली balls भी आएंगी, because after all these fancy F balls, they are also containing A, because their intersection contains A, so they are containing A. In fact, their intersection is equal to A. Equal to A means contains A. ठीक है, so fancy F is contained in boldface B sub A. अब आप ये देखिए, व्हाट इफ आई टेक, देयरफॉर ये हो गया, बस इसमें इतना ही है. देयरफॉर अगर आप ये लेंगे, इंटरसेक्शन ऑफ ऑल द बॉल्स इन fancy F, this will be, you are taking intersection, right? And if you take intersection of all the balls in boldface B sub A, since boldface B sub A is a bigger collection, तो यहाँ ज़्यादा balls आएंगी और आप intersection ले रहे हो, so that means ज़्यादा restrictions. So that is the reason the intersection of all the balls in fancy A, it will be containing the intersection of all the balls in boldface B sub A. But this we know that this is equal to cover of A by definition. ठीक? And what is this? This is actually because fancy F is this collection, and intersection of all the balls in fancy F means this intersection, which is equal to A. So that means we have this. So A is containing the cover of A. A is containing its cover, and cover is already contained in a cover already contains A, so therefore we have the equality. ये आप यहाँ incorporate करेंगे. फिलहाल आप देख रहे हैं A is containing the cover, but cover of A is already containing A. That's the definition. So we have actually equality. So A is equal to cover of A, so that means admissibility. Consequently, this A is a bounded admissible set. Admissibility तो यहाँ से जो हमारी admissibility definition है उसके हिसाब से A should be equal to the cover of A. ठीक, तो वो तो हो रहा है, A is equal, but boundedness कैसे आ रही है? ये बता सकता है आप में से कोई? It's a bounded admissible set.
Intersection of balls है तो
हाँ, तो it will be contained in the balls. Contained in a ball means boundedness. In fact, ये चीज़ अगर आप चाहे तो ये प्रूफ में भी यहाँ लिख सकते हैं. इसको आप इस तरह से यहाँ एक लाइन ऐड करनी है, आप लिखेंगे clearly A is bounded. A is bounded full stop, फिर बाकी ये चीज़ जो हमने लिखी है ऑलरेडी. तो एडमिसिबिलिटी को आप ऐसे भी कैप्चर कर सकते हैं. एक रिक्वायरमेंट, ये क्राइटेरिया देखिए एडमिसिबिलिटी का. You just actually you should be able to, if you can do this, if you can write your A as an intersection of certain closed balls, अगर आप इसको लिख सकते हैं as an intersection of certain closed balls, then it is admissible. In fact, it is bounded admissible. ठीक. So essentially we have two definitions for, because ये चीज़ को भी ना actually ये है कि by the way, is the converse of this theorem true? ये स्टेटमेंट देखिए और अपने आप से पूछिए, इज द कन्वर्स ट्रू?
yes sir.
कन्वर्स इज ओबियस है ना. So it's an if and only if theorem. So that means you can treat this as an admissibility definition. You can treat this as an alternate admissibility definition. Because if A is bounded admissible, bounded means B sub A will be non-empty. The collection of all possible closed balls containing A will be non-empty. And admissibility means the intersection of all those balls will be A. So that means again you can write A as an intersection of certain closed balls. So obviously the converse is true. So it's an if and only if theorem. So therefore I can use this जो information यहाँ है ना यहाँ से I can frame an alternative or I can formulate an alternative admissibility definition. और वह alternative definition क्या होगी? If you can write the set as intersection of certain closed balls, then that set will be bounded admissible. It will be bounded and admissible. अब यहाँ से आप कुछ चीज़ ना इमीडिएटली देख सकते हैं विद द हेल्प ऑफ दिस थियरम. वो ये पहली ऑब्जर्वेशन, एवरी क्लोज्ड बॉल इज एडमिसिबल है या नहीं? आप देख पा रहे हैं इसको कैसे? On what basis I am saying that every closed ball is admissible?
इंटरसेक्शन है, मतलब एक ही सेट.
हाँ, if you take a closed ball, take its intersection with itself, so you can see a closed ball has an intersection of closed balls. So therefore by the above theorem it's admissible. ठीक है? दूसरी चीज़, इनफैक्ट दिस इज़ ऑब्वियस, ये है ना, इसके लिए आपको ये थियरम की मदद की ज़रूरत नहीं है. वो ये है कि आर्बिट्री इंटरसेक्शन ऑफ admissible sets is an admissible set. Arbitrary intersection of admissible sets arbitrary intersection of admissible sets is an admissible set. Third observation, और वो ये है यूनियन. What do you think of the union? यूनियन के बारे में क्या ख्याल है आपका? If you take union of two admissible sets, it क्या लगता है आपको? It need not be. It need not be an admissible set. और इसको जस्टिफाई करने के लिए आई जस्ट नीड एन एग्जाम्पल, और मैं आपको वही दे रहा हूँ. यू कंसिडर A equal closed interval closed interval आप लेंगे 4 2 यहाँ से 2 6. you take A as this and B as closed interval 8 12. now this A you can write this as the closed ball. A1 A2 करिएगा, मुझे थोड़ी सी ना दिक्कत होगी फिर नोटेशन में. आप सेट्स को डिनोट करेंगे बाय A1 and A2. A1 and this set is going to be A2. now A1 देखिए, अब I can write this A1 as the closed ball whose center is 4 and whose radius is 2. ठीक है ना? Likewise ये जो है A2 I can write it as the closed ball whose center is 10 and whose radius is 2. ठीक. So ये किया जा सकता है. अभी हमने देखा every closed ball is admissible, so A1 A2 are admissible because you can see these A1 A2 as closed balls in R with usual metric, so they are admissible in the real line. ठीक. What about their union? If you take the union A1 union A2, this will be 2 6 union A12, and this set is not convex. है ना? It's not convex because it's disconnected. It's not an interval. It's not convex. Whereas in R, every admissible set is convex. ये देख सकते हैं आप कैसे? अब मैं से कोई बता सकता है मुझे कैसे? इसका सिंपल सा रीजन है. Admissible set means A is equal to the cover. In fact, this is a bounded set also, so I can use some stronger arguments. और वो ये है, मैं ऐसी ज़बानी बता रहा हूँ आपको. You imagine an admissible set in R. R की मैं बात कर रहा हूँ. Imagine an admissible set in R. Bounded admissible set. ठीक. Bounded admissible अगर है तो आप इसको लिख सकते हैं as intersection of balls. Now balls are convex sets in R. Every ball in R is convex. है ना? Because R after all is a normal linear space, और normal linear spaces में जो balls होती है they are convex sets. ठीक. Every ball is convex. Admissible set can be written as intersection of balls. Balls are convex, so basically admissible set in a way can be seen as intersection of convex sets. मैं R की बात कर रहा हूँ. And intersection of convex sets, we know that it's a convex set. ठीक है ना? It's a convex set. So every admissible set in R, every bounded admissible set in R is a convex set. Now that this set is not convex, so it cannot be admissible. So this is an example of two admissible sets whose union is not admissible. Not convex and therefore not admissible also. बाकी सेटिंग्स में ये ज़रूरी नहीं है. एडमिसिबिलिटी जो है ना, इट नीड नॉट इम्प्लाई कॉन्वेक्सिटी बिकॉज देयर मे नॉट बी एनी मीन्स टू चेक द कॉन्वेक्सिटी. लेकिन यहाँ आना चूँकि ये जो है इट्स नॉट कॉन्वेक्स, सो इट्स नॉट एडमिसिबल. नॉट कॉन्वेक्स एंड देयरफॉर नॉट एडमिसिबल. ठीक है. So I have justified my assertion that union of two admissible sets need not be an admissible set. Now the question is why we are interested in these admissible sets. Why we are interested in this? इसका एक फ़िलहाल मैं, हालांकि इसमें अभी ये पूरा मैं आपको नहीं दिखा सकता कंप्लीट पिक्चर, बट एटलीस्ट थोड़ी एक पार्शियल इन्फॉर्मेशन या पार्शियल आंसर मैं इसका आपको दे सकता हूँ. Actually you can decide the completeness of the space using the bounded admissible sets. वो कैसे, वही मैं आपको अब दिखाना हूँ. You write this as a theorem. Let XD, it's a theorem. Let XD be a metric space. Full stop. If every decreasing sequence of non-empty sets if every decreasing sequence of non-empty sets in script AX, where script AX is the collection of all possible bounded admissible sets of X, bounded admissible subsets of X. If every decreasing sequence of non-empty sets in this has a non-empty intersection, अगर ऐसा है intersection, then it turns out the space XD is a complete space. ठीक है, अगर ऐसा है, if this be the case, then we can conclude that this XD is a complete space. But the condition is this: every decreasing sequence of non-empty sets in AX must possess a non-empty intersection. So that means if you assume this, every decreasing sequence of non-empty sets in AX has non-empty intersection, if you are assuming this, then you can actually claim completeness of the space. And basically this ensures completeness. अगर ऐसा हो रहा है, then space is complete. Now let's prove this. Proof. Proof is easy, ज़्यादा difficult काम नहीं है ये. आप क्या करिए, we start with the Cauchy sequence. We have to prove completeness, so we'll begin with the Cauchy sequence, that xn, n running from 1 to infinity, be a Cauchy sequence. Be a Cauchy sequence in xd. First up, इसके बाद आप क्या करिए, for each n in the set of natural numbers, we define certain things. ठीक है, for each n in the set of natural numbers, define. पहली चीज जो हम define करेंगे वो एक set होगा. It will be denoted by a sub n. a sub n मैं किसी और चीज के लिए इस्तेमाल करना चाहूँगा यहाँ. I'll be only taking the. अब देखिएगा if you can make sense of this. हम एक ही चीज़ define करेंगे और बहुत जो दो उसके बाद इस्तेमाल करेंगे. Define हाँ वो बेहतर होगा मेरे ख्याल से. You define r sub n. मैं बस आपको r sub n बताऊंगा कि क्या है. You define r sub n as the this r sub n is going to be a diameter of certain set. मैं वही सोच रहा हूँ पहले वो set introduce करूँ या directly ये, हालांकि we'll be only working with these diameters. चलिए ऐसा करते, एक मिनट. Define एक step extra लिखने में कोई ज़्यादा मसला नहीं है, तो so define, first we define s sub n. What is this s sub n? मैं आपको बता रहा हूँ. Define s sub n as the set of all the terms in the sequence, including and after the nth term. That means it is going to be xn, comma xn plus 1, xn plus 2, and so on. ठीक है, so this is Sn, and यहाँ हम एक और चीज़ अब डिफाइन हम करेंगे, वही Rn, and Rn will be defined as R sub n. It will be defined as the diameter, जिसको हम डेल्टा से डिनोट करते हैं, the diameter of Sn. ठीक, and we know what is diameter. Diameter is actually the sup. क्या करना है, you have to take sup of distance between xi, xj, such that I comma j they should be greater or equal to n. ठीक है? This is the diameter. And this will be Rn. Full stop. अब ये this will be a simplifying assumption. Now if this sequence xn जो हम ऊपर ले रहे हैं, if this sequence xn has finitely many distinct terms, has finitely many distinct terms, तो फिर क्या होगा? If it has only finitely many distinct terms, then it will be eventually constant and therefore convergent. Then xn n running from 1 to infinity is clearly convergent. Is clearly convergent, full stop. So we'll be assuming what? So we'll assume, because this actually turns out to be the trivial case then. So we'll assume sequence xn n running from 1 to infinity has infinitely many distinct terms. Has infinitely many distinct terms. Infinitely many. Distinct terms. Full stop. ठीक, बस हो गया ये. We're almost done. अब आप क्या करिए? For each n, again, for each n in the set of natural numbers, you define something. You define a sub n. ये देखिएगा कि क्या हो रहा है यहाँ. A sub n, I am defining as, you have to be very careful with this. It is defined as intersection I runs from 1 to n, closed ball B xi, center is xi, the ith term in the sequence, and the radius is going to be ri. वही rn जो है ना ऊपर जो आप डिफाइन किए वही है ri, which is actually diameter of si. तो ये है. Now what can you tell me about these ans? अभी जो हम theorem देख रहे थे उसमें हमने देखा if you can write a set as an intersection of certain closed balls, then that set is an admissible set. If A can be written as an intersection of certain closed balls, then A is bounded admissible. अब these ans हम इनको लिख रहे हैं खुद से ही as intersection of closed balls, so each an is bounded admissible. ठीक है? कुछ और आप बता सकते हैं about these ans? Decreasing obviously, because an जो है ना उसमें आप n balls ले रहे हैं, an plus में उन्होंने n plus 1 balls आएंगे, और वो जो n plus 1 की जो वो पहली n balls होंगी वो वही होंगी जो an में आ रही है. That is the reason these ans are also decreasing. So it's a decreasing sequence of bounded admissible sets. हमारी जो assumption है उसके लिए क्या क्या चाहिए आपको असल में देखिए. We are assuming this every decreasing मिल रहा है हमें, admissible में मिल रहा है, ax में भी ये होंगी. Bounded admissibility तो हो रही है because they are intersections of balls, so they are bounded also. So they are in ax, these ans. But what about the non-emptiness? How these ans are non-empty? ये बताइए मुझे.
AN will contain SN.
AN will ये ठीक से देखिए आप. इसका रीज़न ये है, और ये वेरिफिकेशन मैं आप पे छोड़ रहा हूँ. असल में रीज़न ये है, if you take this B, if you take a ball, जो ये इंटरसेक्शन में ये बॉल्स आप देख रहे हैं ना, कोई एक बॉल उठाइए, BXI RI, ठीक है. Do you know that, yeah, you can actually see this easily, that this ball, it actually contains all the points in SI. This is the reason. BXIRI, it contains all the points in SI, and so therefore if you take the intersection, if you take the intersection of these balls, I running from 1 to n, क्या से आप शायद सही कह रहे थे, this will contain this XIRI, this will contain intersection I runs from 1 to n SI, and intersection I runs from 1 to n SI, I think that it will be equal to SN, huh? Because these SNs are also decreasing, so that is the reason. आपका क्या आंसर सही था फिर. So AN is actually containing SNs, and these SNs will be actually infinite sets, जो हमारी वो assumption है ना ऊपर जो हमने लिखा था यहाँ. Without loss of generality, we are assuming that XN has infinitely many distinct terms. ये लिखा है हमने, इसको हमने ensure किया है, we can assume this has infinite. Under this assumption, these SNs are actually infinite sets. ठीक है. So clearly these ANs are also non-empty. बस ये आपने किसी तरह से ensure करना है. BXI RI contains SI, and this is also easy. कोई ज़्यादा difficult, because RI after all is what? It's actually the diameter of SI. ठीक है. And XI is a point of SI. In fact, it is the first point in SI. So this is the reason that this ball will be containing SI. So AN, which is the intersection of these balls, will be containing intersection of SIs, which is SN. ठीक, मैं यही अब लिखने जा रहा हूँ. We define ANs like this. Then this the sequence of these ANs. Then AN running from 1 to infinity. The sequence of these ANs is a decreasing. It's a decreasing sequence of non-empty sets in script AX. ठीक. So therefore by our assumption क्या होगा? Our assumption is this: every decreasing sequence of non-empty sets in AX has a non-empty intersection. Now that this is a decreasing sequence of non-empty sets in AX, so therefore by our assumption it must have a non-empty intersection. Therefore by our assumption, the intersection of all the ANs will be not phi. ठीक है. Now that the intersection is not 5, so I could pick an element from the intersection. अब यहाँ हम वही करेंगे. So you pick an x in the intersection and running from 1 to infinity an. Then this x, it belongs to all the an's because it's in the intersection. And what is an? An is intersection of first n balls, these balls. ठीक. X belongs to all the an's. An is intersection of first n balls. So that means x belongs to all these balls. Full stop. Consequently, this x, it must be in all the balls. It must be in B, xi, ri, and it must be true. ठीक है, ये देख पा रहे हैं आप कैसे? इसको ऐसे भी आप एक्चुअली ना, हालांकि ये भी सही है, या इस तरह से भी देखा जा सकता है. x इज इन an इज द इंटरसेक्शन ऑफ दीज बॉल्स, और इन बॉल्स में जो आखिरी बॉल होगी, द nth बॉल, which will be actually bx and rn, so it means x belongs to bx and rn, and since x belongs to an for all the n, so that means x belongs to bx and rn for all the n's. ये भी ऐसे भी देखा जा सकता है. मैं यही लिखूंगा, I'll write x and rn because that is more ना, we are more comfortable with that. X belongs to B, X, N, R, N. And this will be true for all the n's in the set of natural numbers. Full stop. Thus, now that if x is in the ball, so what would be the distance between x and the center of the ball? It will be less or equal to Rn. And this will be true for all the n's in the set of natural numbers. अब पता है हम क्या करेंगे? We'll let this n go to infinity. और आगे की कहानी आप मुझे बताएंगे उसके बाद क्या होगा. Letting n go to infinity, and if n goes to infinity, what happens to Rn's?
जीरो को जोड़ो.
वो जीरो क्यों जाएंगे जीरो को? It's a Cauchy sequence. मैं यही लिख रहा हूँ, letting n go to infinity and noting that Rn's go to 0 as n goes to infinity. We get what? We get the sequence xn, because the distance between the nth term and this point x is less or equal to Rn. Rn goes to 0, so by squeeze principle the distance in the limit will be 0, so the nth term is going to x. That means the sequence xn is converging to x. And that means completeness. Hence, XD is a complete space. और बाय द वे, हालांकि ये चीज़ हमें यहाँ नहीं चाहिए, बट बाय द वे मैं आपको ये बता रहा हूँ. Is it possible to find another x in this intersection? ये जो मैं यहाँ ले रहा हूँ, pick x in the intersection, क्या यहाँ कोई और x आ सकता है from this intersection?
No, sir.
नहीं. क्यों? Because sequence limit is unique. आपने जो x यहाँ लिया ना, आप eventually देख रहे हैं this x is actually going to be the limit of the sequence xn, and since sequential limit is unique, so यहाँ और कोई point नहीं हो सकता. तो actually ये जो intersection है यहाँ, this will be a singleton set. हमारे केस में ये जो ans हमने create किए ना, इनका जो intersection होगा, it will be actually a singleton set. इसमें कोई दूसरा point नहीं आ सकता. बस अगर दूसरा पॉइंट होगा तो बाय these arguments वो पॉइंट भी फिर लिमिट होना चाहिए xn का, बट वो मुमकिन नहीं है. In a Hausdorff space, a sequence converges to a unique limit if it converges. So ये completeness को हम ऐसे भी capture कर सकते हैं. And the requirement is every decreasing sequence of non-empty sets in AX must have a non-empty intersection. और ये जो property या ये जो property जिसको हम यहाँ as an assumption ले रहे हैं ना इस theorem में, this property of AX, that every decreasing sequence of ये AX वाली प्रॉपर्टी ना जिसका इस्तेमाल करके हमने ये कंप्लीटनेस एंश्योर करी, या जिसका इस्तेमाल करके हमने XD की कंप्लीटनेस को दिखाया, मैं फिर से वही कर रहा हूँ. दिस AX प्रॉपर्टी ये जिसको मैंने यहाँ ये एनक्लोज किया, this AX property is called the compactness of AX. We say AX is compact if this thing happens. And if this thing happens, it means space is complete. So that means in this terminology, compactness of AX, it guarantees completeness of XD. मैं ये definition record कर रहा हूँ अब. यहाँ पे स्टार्ट करेंगे, ये लैग हो रहा है. Compactness of script AX. Let XD be a metric space and AX be the collection of all possible bounded admissible sets in XD. Then this collection script AX is said to be compact as compact if and only if every decreasing sequence of non-empty sets in AX has a non-empty intersection. अगर ये हो रहा है, if every decreasing sequence of non-empty sets in AX has non-empty intersection, we say AX is compact. और ऊपर वाली थियरम को जो अभी हम थियरम देख रहे थे, अगर आप उसको rephrase करेंगे in this terminology, so you can conclude this: AX is compact implies the space is complete. If AX is compact, then XD is a complete space. ठीक है, ये वाली टर्मिनोलॉजी में हम completeness को ऐसे कैप्चर कर सकते हैं. You require compactness of AX. Where by compactness we mean this: every decreasing sequence of non-empty sets in AX must have a non-empty intersection. अगर ऐसा है, we say AX is compact, and this means जो अभी हम देख रहे थे by the theorem, it means XT is complete. ठीक है. अब में से मुझे कोई बता सकता है why this property is called compactness of AX? इस प्रॉपर्टी को compactness क्यों कहते हैं हम? Every decreasing sequence of non-empty sets in AX has non-empty intersection. Why this property is called compactness?
सर ये FIP जैसी
एग्जैक्टली ये FIP के जैसे आप इसको शक्ल दे सकते हैं. एग्जैक्टली FIP नहीं है, बट FIP के जैसे आप इसको ना, यू कैन मोल्ड इट, रादर रीमोल्ड इट इनटू द FIP फॉर्म. फाइनाइट इंटरसेक्शन प्रॉपर्टी वाली शक्ल आप इसको दे सकते हैं. हालांकि ये हमारे लिए रेलेवेंट नहीं है, बट ये आपके लिए जानना ज़रूरी है ना, इसको क्यों हम कंपैक्टनेस कहते हैं इस प्रॉपर्टी को. आप क्या करिए, अस्यूम ऐसे आप करिएगा, अस्यूम फैंसी F इक्वल हाँ यहाँ लेकिन बहुत सारी चीज़ें इस्तेमाल होंगी, मे बी ज़ुरान स्लेमा भी इस्तेमाल होगी यहाँ. I'll only take the countable case. Assume fancy F equal AI, where I varies over the set of natural numbers, is a collection of script A X members. It's a collection of script A X members such that every finite collection of fancy F members has non-empty intersection. Every finite collection, rather sub-collection of fancy F members has non-empty intersection. So we are assuming this. अब आप क्या करिए इसके बाद, for each n in the set of natural numbers, you define Bn like this. You define Bn as intersection I runs from 1 to n A sub I. Then if that be the case, then Bn n running from 1 to infinity Bn n running from 1 to infinity is a decreasing sequence. है ना, decreasing is a decreasing sequence of non-empty script A X members. Because arbitrary intersection of script A sub X member, script AX members is an AX member. ये भी है ना intersection of AX members, so it will be every Bn is an intersection of AX members. So every Bn will be an AX member. So Bn's are AX members. Bn's are decreasing also, and Bn's are non-empty also. क्यों? Because about fancy F we are assuming this every finite sub collection of fancy F members has non-empty intersection. Since these AIs are running from 1 to n, they actually they make up a finite sub collection of fancy F members, so their intersection will be non-empty. So therefore bns will be non-empty. So bns में ये चीज़ है, if you consider sequence of bns, it is a decreasing sequence of non-empty AX members, and therefore if you go by this property of AX, if you assume that AX has this property जिसको हमने compactness नाम दिया, if you assume that AX has this property, every decreasing sequence of non-empty sets in AX has non-empty intersection, अगर आप ये assume करते हैं तो यहाँ से फिर आप मुझे क्या बता सकते हैं? From this then we can conclude that intersection of bns will be not phi. ना अगर आप ये प्रॉपर्टी जिसका नाम हमने compactness दिया है, ये प्रॉपर्टी अगर आप assume करते हैं, if you assume every decreasing sequence of non-empty sets in AX has non-empty intersection, so in particular the intersection of bns will be non-empty also, because after all bn sequence is also a decreasing sequence of non-empty sets in AX. So this will be not phi. But what is intersection of these bns? Well, this is actually intersection of all the fancy F members. This is actually intersection I runs from 1 to infinity a sub I, जिसको ऐसे भी लिखा जा सकता है, intersection a varies over fancy F. ठीक है ना? Because fancy F is this. और bns का intersection, जब सारे bns का intersection आप लेंगे, it will be intersection of all the AIs. It is because of this description of these bns. जिस तरह से हमने ये bns को define किया ना, this will ensure that intersection of all the bns will be intersection of all the AIs, which is intersection of all the members in fancy F. So basically intersection of all the members in fancy F will be not phi. So under this assumption, जिसको हमने compactness नाम दिया, under this assumption you can show that every collection, यहाँ तो मैं countable ले रहा हूँ, but you can actually extend the arguments to the arbitrary collections also. So basically you can show that every collection of AX members with FIP has non-empty intersection, because जैसे यहाँ दिखा रहा हूँ ना आपको fancy F members का जो intersection it's not phi, तो यही चीज़ जो है ना आप इस्तेमाल करके आप basically you can show that if this is true, if every decreasing sequence of non-empty sets in AX has non-empty intersection, then you can actually show that every collection of AX members with FIP has non-empty intersection. And this thing sounds like FIP. In fact, वो compactness की जो FIP characterization है, ये कुछ ऐसा ही लगता है फिर. And it is because of this reason that this property is called the compactness. जैसा कि वो लड़की ने ना वो point out सही तरह से किया था, हालांकि ये डायरेक्टली FIP जैसा नहीं लगता, बट आप इसको ना वो FIP वाली शक्ल इस तरह से दे सकते हैं जैसे मैं यहाँ कर रहा था. ठीक है, अब फिलहाल के लिए हमने अब ये हमें पता है इफ दिस इज कॉम्पैक्ट. कॉम्पैक्टनेस यहाँ से, कॉम्पैक्टनेस से हमारा मतलब यहाँ ये होता है एवरी डिक्रीजिंग सीक्वेंस ऑफ नॉन एम्प्टी सेट्स इन AX हैज नॉन एम्प्टी इंटरसेक्शन. और अगर ऐसा है, इफ इट इज़ कॉम्पैक्ट देन स्पेस इज कंप्लीट, जो अभी मैं आपको दिखा रहा था. अब ख्याल से आज के लिए काफ़ी है. हाँ, मैं आपको एक एक्सरसाइज देना चाहता हूँ, यू ट्राई दिस. दिस अगेन पॉइंट्स टुवर्ड्स द इम्पोर्टेंस ऑफ दीज एडमिसिबल सेट्स. पहले कलर चेंज कर रहा हूँ. ये आप इजीली देख सकते हैं. नॉट एवरी सबसेट ऑफ अ हाइपर कॉन्वेक्स स्पेस इज हाइपर कॉन्वेक्स. मतलब ऐसे है, इफ XD is hyperconvex and y not equal to phi, is a part of X, then the subspace YD, this need not be hyperconvex, need not be hyperconvex. We know this. In fact, ये हम दिखा भी सकते इसके लिए. There are examples. R is hyperconvex, and if you take y equal to, अभी जो हम वहाँ वो देख रहे थे ना, जो यूनियन करके A1 A2 का जो यूनियन आया था, अगर आप उसी को y लेंगे, वो क्या आया था वहाँ बाय द वे, शायद ये था 2, मुझे पूरा याद नहीं है, 2 6 यूनियन 8 12. If you take y as this, then y with the usual metric is not hyperconvex. Although this y with usual metric is a subspace of R with usual metric, and R with usual metric is hyperconvex. However, R with usual metric, which is a parent space of this, is hyperconvex. However, this is hyperconvex. So the moral of the story is, not every subspace of a hyperconvex space is a hyperconvex space. ये hyperconvex क्यों नहीं है, by the way, कोई बता सकता है आप में से? Why this y with usual metric, where y is this, is not hyperconvex?
It is not metrically
It's not
convex.
metrically convex. In fact, ये R में hyperconvexity and convexity, they are same. में कोई फर्क नहीं है. It's not convex, so it's not hyperconvex also. You can, if you take a point 6 in y and 8 in y, is there any point in y which is metrically between 6 and 8? नहीं, कोई point है ही नहीं. It's not metrically convex, जैसे कि मंसूर ने बताया था. So it's not hyperconvex. So the moral of the story is, not every subspace of a hyperconvex space is a hyperconvex space. Now the question is, which subspaces of a hyperconvex space are hyperconvex? इसके लिए मैं आपको एक एक्सरसाइज दे रहा हूँ. इस एक्सरसाइज में असल में इस क्वेश्चन का आंसर है. किस क्वेश्चन का आंसर? यही जो मैं भी पूछ रहा था आपसे. Which subspaces of a hyperconvex space are hyperconvex? Because not every subspace is hyperconvex. वो तो अभी हम देख रहे हैं by means of this example. Not every subspace is hyperconvex. So the question which becomes interesting here is, which subspaces are hyperconvex? और उसका आंसर ये एक्सरसाइज में है, ये आपने दिखाना है. Let XD be a hyperconvex space and y not equal to phi be in script AX. That means y is a non-empty bounded admissible subset of X. If that be the case, then the subspace YD, ये आपने दिखाना है, then show that YD is also hyperconvex. This would be an exercise for you. Try करिएगा इसको. And the hint for you is that you have to use the inheritance principle. आपको YD की hyperconvexity दिखानी है. So you'll start with a collection of closed balls in YD satisfying that property. Distance between the centers is not exceeding the distance between the associated, is not exceeding the sum of the associated radii. In order to prove hyperconvexity of YD, you'll start with a collection of closed balls in YD in which the distance between the centers is not exceeding the sum of the associated radii. वही करते हैं ना हम, and we'll eventually show that the intersection of all those subspace balls is non-empty. अगर ये आपने किया, the subspace will be hyperconvex. अब सबसे पहली चीज आप इनिशियली जो आप बॉल्स इंट्रोड्यूस करेंगे, दे विल बी सबस्पेस बॉल्स. आप क्या करेंगे, वो सबस्पेस बॉल्स को आप कनेक्ट करेंगे विद द पेरेंट स्पेस बॉल्स, बिकॉज पेरेंट स्पेस के लिए आफ्टर ऑल वी नो दैट द पेरेंट स्पेस इज हाइपर कॉन्वेक्स. दिस इज द मोटिवेशन फॉर कनेक्टिंग दीज सबस्पेस बॉल्स विद पेरेंट स्पेस बॉल्स. और वहाँ आप किस चीज़ का इस्तेमाल करेंगे, यू विल यूज द इनहेरिटेंस प्रिंसिपल. और फिर देखिएगा कि कैसे आप ये पेरेंट स्पेस हाइपर कॉन्वेक्सिटी और वाई की एडमिसिबिलिटी, ये आपने देखना है कि हाउ यू कैन यूज दीज टू थिंग्स, पेरेंट स्पेस हाइपर कॉन्वेक्सिटी एंड एडमिसिबिलिटी ऑफ वाई टू शो द हाइपर कॉन्वेक्सिटी ऑफ सबस्पेस. सो इट्स एन एक्सरसाइज. इसके लिए हिंट है, 3 हिंट्स मैं दे रहा हूँ, यही जो मैं ज़बानी आपको बता रहा था. पहली चीज़, यू हैव टू यूज़ द प्रिंसिपल ऑफ इनहेरिटेंस. दूसरी चीज़, हाइपर कॉन्वेक्सिटी ऑफ XD इज हाइपर कॉन्वेक्स. और तीसरी चीज़ जो आपने इस्तेमाल करनी है होगी तीसरी चीज़ जो आपने इस्तेमाल करनी है वो ये है, वो ये फैक्ट है कि दैट दिस वाई इज़ एडमिसिबल. तीसरी चीज़ आप यूज़ करेंगे, वाई इज़ बाउंडेड एडमिसिबल. हिंट्स, ठीक है, ये देख लीजिएगा. अगर कोई दिक्कत आई तो फिर मुझे कल बताएंगे आप. बाकी इंशाल्लाह कल देखेंगे आप. कल भी ऐसे ही 10 बजे या उससे पहले ही, शायद 9:30 मैं ये स्टार्ट